I hear somebody has birds outside.
I have maybe mine window. I am home, and
Nice.
yes, the window is open. So
It's better than the marching band. Does the marching band still practice outside your
it
windows?
has been a while because of COVID.
Yeah.
Yeah, I don't know, but I imagine when everything starts normal, I will have the concert every Friday.
Yeah, it would be right now, right? So you're
Yes, 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 great. So students are starting to join, but maybe let's wait 3 more minutes and we start. Mhm.
Very good. So how many, when is the last week of the school? Is that already, or is it another week?
Two more weeks. Yes, it's
Tomorrow?
4 weeks.
No, 2 more weeks.
Yeah,
2 more
yeah,
weeks.
Yeah,
Okay.
yeah,
Okay. Okay. So students still have, okay.
yeah.
yes,
It's a long
students.
school.
No holidays for the students. Yeah, we
No.
are talking here about the holidays, and they,
Well, but here the vacations are very long, so there is still some time in August. I mean, we start only, I think, the third or last week of August, so not the third week.
Yeah,
So,
sure. No, for the real studies, well, I was thinking about the school here, our school, so they have to study there. They cannot go
yes,
on
exactly.
holiday.
But they have 1 week after it's done. They could have 2 weeks of vacation if they want to. I
Except
think.
the
Okay.
European students.
The European students. Oh, sorry. Okay. Yes, I see.
Now,
Yes.
the ETH students, they anyway, they always have this. All the exams are just before the next term starts. So it's
Oh
a bit.
no.
Yeah. It's
Oh,
I don't know. It's not really fair on them. I should not publicly say that here.
Wow. Yeah.
But
Yeah.
at some point they have to learn the stuff. So well.
Yeah. That's true. Yeah. Yeah. Yes. I mean, this is also fun. I think is interesting. So it's hopefully it's stimulating for them. Mhm. Although it would have been a very different experience in person. Yes, that's the
Oh
bad
yes,
part.
of course.
That's a
Yeah,
huge
sure. But
difference.
well, a bit of a feeling I get here when I chat with you here. That's really nice.
Yes.
and our schedule's busy here, but it's not too grueling, right? We have 3 or occasionally 4 talks a day, 5 days a week. So there's a weekend, there are evenings, there are breaks, but it definitely, it'll wear you out after 4 weeks of this. So.
Oh, Jesus. Yes. A lot of Zoom. For me, Zoom is really tiring. I don't know why. Mhm. Is
Yes, I agree. No, Zoom is only a certain amount one can digest.
Yes. Okay, so let me start. So let me just mention that we have the continuation of very nice lectures by Tilman, and we have I mean, this is the session of we have. Well, I would let Tilman to tell us what is the third lecture of today, the topic of the third lecture.
Okay. Great. So it's nice to be here anyway, and to have been able to join this school. And today we will have this mixed approach, some bit more formula oriented topics, and those are now kind of, I hope, motivated by what we've seen last time, that you can, for example, engineer topological systems and in shaken lattices. So we will look a bit more at lattice shaking. And then we will also look at a way how you can engineer complex phases in Hubbard type of systems, which depend on the density. So where basically you have operators where your phase in the hopping matrix element is an operator rather than just a classical phase. But first, let's look at how is it done when you want to have for example, a complex hopping phase, and how one can treat these lattices. Okay, so in general, you should have, I mean, these are available, what I wrote down here, so you can have a look, of course, online, so you don't have to note it down, everything.
Tilman, just to check, these are the same lectures.
It's the same like last time, and there's no update compared to yesterday, yes. Yeah. So, but nevertheless, try to follow as if you had to write. So, and what I did write down here is the Hamiltonian with the lattice potential. So this lattice potential, and the change here, or the addition, is that it's periodically moving, and that's by this term. And then the usual way how that is treated is, so now we can apply the formalism that we had last time, and one kind of, you can do successively two type of rotations, or going into rotating frames. Sometimes it's sufficient to do one, sometimes a second is even more, makes the physics even more obvious, but it's of course just a change of frame. And the first one, that's typically called a rotating frame, so the unitary transformation that is written down with this operator here, which acts on the momentum. And if you apply that to this Hamiltonian, okay, and it's explicitly written down here, then you get a Hamiltonian of the following form, of this form, where you again have your static lattice, and where you see a change now is in the momentum. There you have, in addition now, a time-dependent term, which is often called or labeled a vector potential, or can act also as a vector potential. In a way, so I think it reflects also the following, and there I also want Anna and Caden to whether I get their agreement or not in this interpretation. I could look at it in the following way. If I periodically move my system, as is done here, my lattice, then my total potential, my potential energy will not change. I don't have an additional potential energy in my system. The only thing that I have in my system is additional motion. So in that sense, it does make sense that another term pops up in the kinetic energy. Okay, so I see you here on the screen, and it seems that there is consent that that makes sense to think of it that way. Of course, one can think of these terms in all sorts of different ways, and different people have different intuitions. Okay, and of course, one has to keep in mind that this term is a time-dependent term, and it goes with the velocity of our position changed potential. And then there is another transformation, which again has this has the probably more intuitive interpretation, that you go into a co-moving frame, so that you go into a frame where you shake along with the lattice, and that you apply in addition with the same type of transformation and the same type of algebra. And then what you end up with is the kinetic energy term. So since you're now moving with the particles, and then you lost that term in the kinetic energy, and you have a time-dependent force. So, which again, if you imagine you are in this lattice, that's exactly what you would expect. And the relation between the time-dependent force and your x2 is obviously, and it's written down here. Okay. And now what you can also do is, well, in these lattices, as we had also discussed last time, there are often, it's sufficient often, but not always, by far not always, and there is lots of interesting physics with higher bands, but one set of physics that you can address is if you restrict to the lowest band. And then you can obviously think of Hubbard-type systems with localized states, and that we had also discussed. So you can think of one-year states in your starting Hamiltonian. And then you have just hopping between neighboring sites. And now you can again go into a co-moving frame or into rotating frames. So both frames, you have the equivalence here. And so the Hamiltonian in the center of mass, or yeah, co-moving frame, you see, well, you have the tunnel coupling, that's where your kinetic energy is. And then you have the time-dependent force, and the position here, x, that is captured, well, by the position. I mean, you have j to you go to somewhere where it's 0, and from there on you count your lattice sites and the spacing. So here you get an x, and here you have your population on, or well, your population on that side. And again, you can also write that in the rotating frame. So one thing you might do is write it that way and then back rotate it, because this Hamiltonian was the consequence of 2 rotations, and now you can take one out again, and then you are in this rotating frame. And in this frame, you have an oscillating phase of the tunneling matrix element. So here you see you have your tunneling, and there you have a phase, and this phase oscillates with this vector type of potential. And you can imagine here already that, okay, maybe one can make engineer some complex tunneling matrix elements, yeah, as we, for example, in the Haldane model needed to break the time reversal symmetry.
In this last, what you call the rotating frame at the end, this is just the gauge transformation, right? Just going from sort of electric field to a magnetic field, or to a time-dependent vector potential.
Yes, yes, yes. Okay, and this is summarized here. Well, it's basically what I said, it's just summarized. And for those who are sufficiently good in French, there are very nice lecture notes by Jean Dalibard about that topic, and it's also in the reference. So even with kind of modest French, or very modest French like my own, it's still one of the nicest references on that topic.
Can I ask a question?
Yes, sure.
So how exactly do these rotations that we're performing relate to the kick operator that we defined previously? Like, are we still, because there we also did.
Yeah, no. These are rotations that I do on my effective Hamiltonian. Then I go to another reference frame.
So you're saying this is already
in the effective one. Yeah, I get the effective, and then I do rotation. I think I was a bit sloppy in what I said earlier on. There was one.
Well,
yeah.
But the effective Hamiltonian that we got when we did this whole Floquet formalism was already time independent, right? But here we have the lab frame Hamiltonian
Okay.
is.
Okay, now you, I'm a bit confused now. Okay, let's look at the time scales. This is, of course, I mean, these kick over, these kick operators, they come in to have an additional, so this is to get the effective Hamiltonian, and because the kick operators, they just are important for the evolution to get the starting point correct. You see, you have some starting point initially that was this. Well, there was this diagram with the, and then you have the full. Then you have the full periods, and the kick operators, they give you that you get correctly this period in time.
Yeah, I guess my question was whether this rotation that we're performing now, whether like to first order or something, this would be the same as what we would get, like whether like R naught of t is the same as like e to the minus I kt.
So it's a rotating frame like you would rotate in a two-level system when you put the rotation into, well, in your so that you get time independent amplitudes.
Yeah. It's like when you go to the rotating frame, you have some field rotating, you get rid of the rotation by going to the rotating frame. It's similar. When you go it's just a unitary transformation that is time dependent, basically, to write the Hamiltonian easier.
Yeah,
then you will get
at this stage. There's no Floquet being done, right?
Nothing. Yes,
doing a rotating frame. So you could go further if this f of tau or f of t is periodic, and then do some Floquet analysis. But we haven't done any of that yet. So the time evolution here, I think, is just the time ordered exponential of this h rotating.
Okay, that makes sense. Thanks.
Okay. So
and now So in the lab, I guess, when you make a measurement, how do you go into the rotating frame, like actually?
That is that's a question of the starting point, and the question: do you have? I mean, can you switch on and off on which time scale? Well, can you measure the time scale on which the system is rotating? So these rotating frames are, of course, to get an easier description, but it's like the two-level systems are always again I think the easiest to imagine. So you may measure normally the population between oscillation between ground and excited state, but then you have in addition, of course, you have the oscillating dipole moment on a much faster time scale. And this oscillation, whether you can measure that or not, well, you need well, you need an experiment which can measure on this time scale. And that's here similar, and here often it can, of course, be whether you, well, you have a comparison, a good comparison, where you can switch on and off, and the shift, say, in a time phase makes a difference for your measurement. That's and we will see we will see an example. Well, at least where we look at the different time scales of a many-body. Yeah, probably we'll see one. Yeah, it depends on. Okay, so I'll speed up and then we'll see one. Okay. Okay. So now let's have a look at the sinusoidal shaking. So let's. I mean, we had not defined what the modulation of the lattice position is. The most simple one is just sinusoidal, and there is one way how to interpret it. It is that, I mean, here it's clear we have our two operators of our effective force. And then there, it's typically when you read the papers about this lattice shaking, there it's always the shaking is characterized by some dimensionless shaking amplitude K0, and that one can think about in a well, rather intuitive way, because I mean, if I shake with a force, I can look at it. Well, I have the force in one direction, force in the other direction, so periodically. And now I can think of, if I want to get the energy scales out of the system. So one energy scale is the offset. Well, say I've drawn it with the maximum amplitude, the offset between two different neighboring lattice sites. So that gives me an energy. And that energy I can compare with the driving energy. So this offset of the neighboring energy relative to the driving energy, that's my kind of dimensionless energy, and that is captured by K0. And well, that's written down here. Okay, and in case you have you have additional terms, and then if you have static terms that are just sums over local on-site Hamiltonians, like for example Hubbard use or energy offsets, then these are not, as long as they commute with your transformation, then you can just add them to your Hamiltonian. And such a Hubbard Hamiltonian in this moving frame is written down here. Okay, and then you can, and that gives now, yes, then now we come back to the question which makes it clearer. And now you can, for example, ask the question, once you have your Hamiltonian, now you can apply the Floquet formalism. And for example, you off-resonantly drive the modulation. So that what does it mean? In our single band, which well, there one needs to be careful, of course. Now I say that my energy scale, so omega is the driving, okay? And T is a kinetic energy scale, U is a scale of the on-site energy. And now I can go into a regime where my driving frequency is large compared to those two. Okay, there I need, of course, to be immediately careful, because to build my Hubbard model, my single band model, I have to be small compared to the energy scale of the band gap. So here it's a bit, one has to be, well, careful. It might come back that if this is too large. Okay.
One question.
Yeah.
Can one think of that bug as a feature in that you can do spectroscopy by shaking the lattice?
Yes.
Oh.
Yes, absolutely. No, you can even you can do fun stuff with coupling to higher bands, because then the higher band you can bring down, and then you can, for example, create ladder structures by coupling the lowest with the next higher band. So no, yeah, absolutely. No, it's I fully agree that it's a case of, yeah, the bug is a feature. Absolutely, yeah. Okay, and now comes in your effective Hamiltonian. If you apply that, and then you get your tunnel matrix element. If you do the time averaging, then, for example, in the lowest order, your tunneling matrix element, that is just given by this zeroth order Bessel function.
So Tilman, maybe you mentioned this and I was just zoned out, but you said this is easy in the rotating frame. Presumably I could do the same analysis in the other frame, but what goes wrong?
What goes wrong in the other frame?
Yeah. Why is it not easy, or what goes wrong? This confused me a lot the first time I saw it, why it seemed to get different answers in the two frames, but.
Well, you tell me.
So here's what I think, but or how I convinced myself to be okay with the fact I was getting different answers, but I welcome expert feedback. So I think it's that you have this oscillating, gradient field, the f of t, the force that you had, and that it's sort of infinitely big at the edges. Yes. So if you want to do some Floquet analysis and perturbatively treat things, it's bad to do that when something's infinitely big. So your terms in your power series, they will be suppressed in powers of 1 over omega, but they'll be times infinity. And so probably there's some subtle issue there. But I'm not sure if that's the right explanation. That's just how I convinced myself to work in the rotating frame.
Well, because the other frame would be the more natural somehow, because you take the energy out in both coordinates in a way, in x and p.
Yeah.
So I've never accepted it up to now. Okay, very good.
Maybe one of the students will look into it and tell me if this is right or if I'm way off base on this.
So maybe I think it's also related to the driving amplitude. This K is also in the order of the driving frequency, which is very large, much larger than, let's say, the bare tunneling amplitude. So maybe this is also one of the reasons why you have to go to the rotating frame.
To the rotate,
to absorb this driving into the driving phases, so that you get rid of this super large driving amplitude effect. I don't know.
Good. Okay, and then so now what I plotted here is, well, there are different Bessel functions. At the moment, we just need the zeroth order, and there, I mean, there you see that your tunneling matrix element changes. So basically, I mean, it changes with the zero order Bessel function, and it changes sign, which there are some nice experiments by Monika Eidelsberg where she used in a subtle way the sign change. In this first round of experiments in your Arimondo's group, where they basically looked at the kinetic energy, and then they would get a measurement where you have just a square, which was sensitive on the square of this matrix element. Okay, and now you can also look at resonant driving, even in the Hubbard system, say if you add a term with an offset or if you have a gradient. And often, again, in the Hubbard system, it's often most easy to think of. So you can imagine you have two sites which are off resonant with each other, which have an energy different delta zero. And now you may, well, there you can see, okay, I can drive it with frequency h omega, but I could also drive it with half the frequency. And then I would see, there are two photons which give me the resonance. And there I would get in my effective Hamiltonian, depending on in which order I expand, I would, well, in this case, to get this process, I would have to expand to accordingly higher order. And here the effective Hamiltonian is written down.
So Tilman, so why would you prefer then the two photon instead of the single photon? Is there a reason?
This is at this point here just shown that well, one has to be, well, one could do, for example, an experiment and you just change the frequency, and then you may see, I don't only see at at omega, but I also see at half the frequency, and then one would have to go back to the your Hamiltonian and see where should that come from. Mm-hmm. And then one sees that. And of course, I mention it here because it will play a role in experiments that I will show in a moment.
Okay.
And the effective tunneling, okay, so then you can write down the effective tunneling, and that is in the correspondingly, well, you get the higher order Bessel functions which were plotted above. And maybe briefly here to this, we looked last time at this artificial magnetic fields in shaken lattices. And what you want there is like an electron in a magnetic field, that it picks up a phase on a circle, well, or on a loop. And so if you go here around here, then you want to have the sum of the phases to be unequal zero. And now you could say, okay, I now drive such a process. I make a tilt, and then I drive with an additional field by shaking in the right way, or having an additional Raman field. And yet I also see if I tunnel to this direction, I pick up a certain phase. In the other direction, I would, if time reversal is not broken, I pick up the minus phase. And then I could end up in a situation where if I go around in a loop, that I actually don't pick up a phase, because I could say, well, I can rotate it out, the phase. There's one phase only, and I can rotate it out. Or it's like an interferometer without the second arm, and then I will also not be phase sensitive. The solution that is done is that you now add, say, well, you have, say, a gradient here, so you have your different lattice side, your offsets between the lattice sides, and now you have another field with which you drive. So, and this field is now deliberately at an angle. So you can imagine this field as kind of a, say, a walking walking wave or a moving standing wave, so which kicks the system, which provides the force. But that you will see that here, I mean, well, at this point, so this I have to overlay, but then your driving phase of the outer field is different here and here. And that way, since in this way you break a symmetry, and then you will get a total, you can enclose a flux, and then you can change it when changing this field. I think this precise or most closely to that scheme, I think that was in Markus Kreiner's lab. But I think that basically the schemes reduce to the fact that you need this, well, in a way, strange angle, and you need to have different driving phases at different points, so that you have a relative phase between here and there.
But Tilman, I think, did he do the shaking? I think it was just Raman assisted hopping, no?
Yes, yes, but that in the end, I think it is the same. I think it all, yeah, I somehow, yeah, came to the conclusion that all these schemes are the same, because in a way the atoms feel a driving potential in some form, either a shake from outside, or I do the shaking with a lattice that is moving through it. That, yeah, it's like,
And
yeah.
do you think the heating is the same too? I mean, is the big with the laser and with the shaking, the heating is similar?
The heating, I think that depends on the specific realizations, and I will come to the heating.
Okay, great.
Yeah, I will come to the heating. I will do my best. Yes.
Can I ask another question?
Yeah,
so
sure.
It seems like in the last Hamilton, just maybe backtracking a little bit, like if I look at just there's a term which is like F of T I population, yeah, for example, over there.
So sorry, where?
Below, I think. I guess I'm just trying to think, like, in this effective Hamiltonian, I basically have some sort of tilt that I could generate by just applying a static gradient.
Yes. Yeah.
I would then modulate. Is the idea?
Yeah. Yeah. Or the shaking acts like a modulation of the tilt.
And the idea is that by doing that optically, I can do it faster and actually shake. And if I try to do
I can do it in the experiment. So, well, there are several ways. Two ways we have used is, well, just shaking the lattice. That would produce, if you have an offset between adjacent sides, intuitively in this co-moving frame, that is like it goes up and down. So that gives you the shaking. Or you could apply a magnetic field gradient and actually oscillate the magnetic field gradient. And what you can do with the magnetic field gradient, a nice aspect is that the magnetic field gradient can be different for one spin than for another spin. And then you can, if you think of just the tunneling here, you can be at 0 for one band, kind of flat band for one spin, and somewhere else for the other spin. That's actually quite cute. We have stuff work on that. Yeah.
So in this picture, the shaking, because it couples to the atom's motion, is always guaranteed to be spin independent.
Yes, otherwise it's spin independent. But here you see, if you think about the Haldane model we had last time, and then if you were thinking about you wanted to make the Kane-Meyle model, there you need two spins, and then that's where we thought, maybe we can do that with this spin-dependent shaking. And in principle, one can do it, but experimentally it turned out, well, our coils were not perfect enough from homogeneity and things like that. But in principle, I think one could do that. It should be possible.
Perfect. Thank you.
Yes. So sorry, Tilman. The last question. So, but for the shaking, when you add the other field that gives you the different phases, so you have to add an extra laser anyway. So you have to do both the shaking and adding and so you need an extra
Yes,
thing.
yes, you need an extra thing, and I think it is really like you need two paths to be able to go two paths from the initial to the final point.
Mm-hmm.
And then you can have on those two paths, you can have, well, pick up different phases. And that's necessary. It's like in the ferrometer. For me, it's always a picture of in the ferrometer. I need two paths, and then I have a defined phase. Otherwise, I can always rotate my phase out. There is, I have a clearer picture in the example which we will discuss. There I have the clearest picture, but I think it's true for all these schemes. Okay, so we were here and that was there. And now we come to the briefly to the two bands that were also mentioned. So that where the bug becomes a feature, and that of course I think you will have, or you had, or Ian Spielman uses that a lot to play with the band structure. One way how to look at it, one could see, okay, so what do I do with the driven two-band model? For example, I could drive with the energy of the gap or of the band gap. And so here on the left-hand side, that is just the band structure of the lowest band of some standard 1D lattice. And now I just add in addition the energy of our potential driving. So this H bar omega at this moment, it's just some mirror somewhere else which is shaking, but this frequency is there. And then one may realize, okay, I hit for a given K or given quasi-momentum, I get my resonance here and there. And that's plotted now here on the right-hand side. But there this extended zone energy scheme is plotted. So I have here the lower band with a higher energy and the upper band with a higher energy. So this could go here as well if I have an additional photon or phonon, and it could also go here. And now I get a crossing, I get crossings here. And if the system couples, so if my shaking has an operator which actually couples those 2 points, then I get a avoided crossing. And then I can simply draw, and in this notability, I can take that and cut it here. And then I just draw my avoided crossing. That's how I made this picture. And then I get roughly the band structure, the changed band structure when I had this driving. And then, of course, you can have a much more complicated, you can have two frequencies and in all sorts of directions. Then you can manipulate the band structure. But this is now a two-band model. Of course, the real Floquet theorists, they say, but there are multi-photon transitions. Well, I have another frequency from here, and that hits, well, somewhere up here a band. That hits, the multi-photon, I can hit other resonances. So I get many, many resonances. And then, if such a multi-band model is calculated for different strengths, so that's a paper from Martin Holthaus, then you get this structure here. You can still see something, that's your lowest band, and now the higher bands come in from above. So these are all higher bands, which then, well, if you increase here the coupling, then you get all sorts of multiphoton resonances, and then, well, your overall band here remains here, kind of is flat, which if you had just a single band approximation, then you would have your Bessel function, and then you would be on the zero of this Bessel function. So you recover, of course, to some extent what you had in also in the single band, but here are all sorts of little crossings or avoided crossings. So one has to one has to look at the fine print of that. But often, since these are so small in energy, of course, they only play a role if your time scale of the experiment is long enough to actually probe these avoided crossings. Okay, so that's this theory that we had last time. So now it says we'll go to PowerPoint. Okay, so I'll switch here now with the screens. Let me see how it works. Stop broadcasting here. And now I need to share the other screen. Share. And now I need to start here. And I need to change where I look at the camera. Okay, okay, that's, I think last time we, and I need you to be up here, on that screen, then it's better. Okay, so this is now just a slide to basically compare the type of physics that you can do with Floquet engineering of lattices. So there is one set, as I said, often is actually done in tubes. So the lattice is a 2D lattice. I mean, these experiments on Harper-Hofstadter and Haldane model, well, some were also done in 3D, but the most of the things were done in 2D lattices. And then, of course, you have all the physics, the Hubbard type of physics. And in a way, the goal still is, but has to some extent been done, to combine those. And there is one thing which would be tempting and nice is actually to have, well, if one starts from the Hubbard side, to have a process, well, where you tunnel and then you say pick up some phase. So we have we had looked at these processes. So you can engineer that you pick up some phase, but it would be really nice if you pick up another phase if there is a particle there, and ideally, a non-trivial phase, not one which you cannot rotate out. So that you have a situation where your Hamiltonian now looks like that I have a tunneling matrix element. As an operator, it might depend on whether there can be a density dependent tunneling. It might be density dependent. That's kind of, you often may have that if you look close enough. And then, but then in addition that the phase is an operator, so that the phase may depend on say whether you have a green atom there or not. So that depends on the matter wave field, and you can now put that into the context of coupling between gauge fields and matter wave fields. So there is a general context, and I assume that Monika Eidelsberger will talk more about that. So I will just mention that there is this relation and the interest. I will do now again a comparison between the classical and what one would want to have to make the coupling between matter and gauge field, or such a mechanism. I mean, there can be different motivations. There can just be the motivation. How can I engineer such a Hamiltonian and without caring too much whether it directly maps to some gauge theory or not? But one can have this matter and the coupling of this matrix element. Here, as I said, we had basically this picture we had before. You just go around and you may pick up a phase. And in the other case, where you can have a quantized gauge field or a density-dependent, but could also a condensed matter physicist would more say a density-dependent Piles phase. That's just a question of language. And you could have it that if you go around in a loop like this, that you don't pick up any phase in the loop. However, you would want to have a situation that you can pick up a phase in a loop if there is an additional particle. And there is the question how one can do that, and there were some also some proposal, and it needs some tunnel engineering, and and in that there was tunnel engineering. That's of course a Swiss thing, and there was some press release, and that even in that tunnel engineering, that thanks to scientific calculations, costly delays were avoided. There was some ETH press release at some point. Okay, anyway, but and these scientific approaches there were also done by, here are some suggestions in this direction also. Well, there are proposals and other work, and of course more work. And we will look at a driven Hubbard model, and we have already seen that. We have seen this matrix, this lattice, and there we will go specifically, well, that is shaking, okay, that was this brick wall potential, and then if you shake that, well, that's the Hamiltonian we are now familiar with. But now to look at our scheme, we looked at kind of a dimerized version, and in particular, we looked at the dimerized version to actually be able to measure the phase between two sides, or whether we pick up a phase or not. And our observables in our experiment are we can measure whether we have doubly occupied sites in our time of flight. We can convert them into a third state and can measure. And we can measure singlets, because we can turn the singlets into doubly occupied sites and then measure. And now the question is, at this point, how could I do a phase. How could I encode somehow a phase that the tunneling matrix elements, the phase of the tunneling matrix element depends on the density on the other side, whether there is a particle on the other side or not. So how could I do that? And that was one answer at least. but are there any thoughts to it? No, it's again. Well, doesn't matter if I show it. but maybe one can have a brief look at it and guess what in which direction it will go. The picture. And then just make some suggestion what's all on that picture. And I don't see the chat here. I have to.
Yes, feel free just to speak up. I mean, go
yes,
ahead.
So speak up or chat or whatever.
So maybe you can repeat just the situation, the values of the parameters and things you're considering here. Like.
Okay. Yes, absolutely. So what we are having here are two sides of a Hubbard band, actually. So these are not two bands. So what is drawn here is are two sides of a Hubbard band. So it's all in Hubbard physics. The side offset is an energy scale delta 0, which most reason for that is just that we have a two-level basis in the end. And then we have an energy scale U. So which is the interaction energy between the red and the blue particles. So these are kind of spin up and spin down. And these dashed circles, they mean kind of that we have a singlet on these two sides. And then
if you have,
yeah.
Sorry. I was just saying that I guess if you have singlet, only then you could have both fermions in the same site, same band. So is it something related to that? And if you don't have a singlet, then you can't do this projection.
Yes. So we and that's well, we can of course have a, well, this is type of a singlet state. Yes, it couples to a double occupancy. Well, we do a coupling of this singlet to a double occupancy on the, say, right-hand side. And the offset here is, well, here could also be a double occupancy. No, there is one in principle, an eigenstate where you have a double occupancy on the left-hand side. But this offset helps us to have a kind of a smaller state space. Yeah. So that we only have to consider the coupling between the singlet and this doubly occupied side. And now what did we try to?
Yes, so energetically, you maybe think about energy scales. What is the allowed process, or what you need to do to
what could I now do? Yeah, exactly. What can I now do when I shake? If I now, I mean, that was in the previous picture. No, a bit earlier here. So this one, that is the side that we saw. And we saw earlier that this whole thing shakes. Okay, that's what the experimental setup. And now the question is, what will happen here if we shake? And we also had said that this shaking is like a force that does basically this in this one intuitive frame, even if we calculate in the other frame later.
So you would have the density-dependent tunneling phases.
Yes, yes, absolutely. You would then shake. Which frequency would you take to shake?
Like as you right here, E equal to 2x bar omega.
Sorry, which frequency?
Isn't it 2 or 1/2 of U?
You would, yeah, you would shake 2h omega. No.
You have also a potential.
You have to be. Yeah, now we have to be okay. One has to be. Has to. I'm just. What I'm thinking here is whether the drawing is really perfect or not. Mm-hmm. So the if you go from this state to that state, you see here, my drawing says this energy is this energy difference. So I drive from this energy, I say the atom is here, I bring it over there, no, and then I have the total U. Now I'm just a little bit confused now about the offset. I'm just at the very moment, I'm a bit confused whether I have to drive with this energy or with the delta or U minus delta. So I guess I have to drive with U minus delta. That's and why the factor of 2? And why what I could argue, okay, I drive here and then I get a density dependent tunneling, and I then look at it as if I had an offset between two sides and I get some Peierls phase, and then I'm happy.
Don't you need a shaking?
I'm happy the next moment because I realize people have done it in the literature before. But that's not enough, yeah? Yeah? Or
what you need to transition both spins. You need a matrix element that moves both particles to the excited state.
Yeah, I mean, it's if I do just this density dependent tunneling, then I can write, if I want, a phase in front of it, but I can just as well rotate that out. So then I have this symmetric case where if I tunnel from this side to the other one, or if I tunnel in the other direction, I just get the minus sign, and then I will not pick up a phase. And now there is something else here. So what could be the reason for that something else? What do I need to do? I mean, there was last time. I think, Grace, you said that we need to break time reversal symmetry. So I mean, I can now, and early on, I mean, we said, okay, we can also drive this process. Well, we can drive it with half the frequency and the frequency. I mean, there's no I mean, I could even add higher orders, so even lower frequency, I could drive this process. If I drive it just with, well, here is the frequency, this is half the frequency, so either I drive a 1 photon or 2 photon process. However, what do I gain if I drive this process with both frequencies? There's one additional thing if I drive it with omega and 2 omega. That's the key point of the whole scheme. What is which parameter do I have?
Going back to your comment, you have 2 paths for which to transition, and you get the interferometry effect that actually gives you a phase to compare.
Yes, I mean, if you have, exactly. I mean, if you have 2 frequencies and which are multiples of each other's, so which are commensurate, then you have a relative phase. And if you then also plot the waveform in real time, then you can see that thereby you can break time reversal symmetry. So and that's where how you can then create a non-trivial time phase in this process, which depends on this on U, because you can only drive you have only this process if you have U. So that's that's the key point of that scheme.
Mhm. So in the Raman beam, this is just associated with the transfer of momentum at a given direction, yes, basically? That is...
Yes, exactly, yeah. Yes. And okay, yes, and then exactly. So that's the total matrix element. Then you need to write, well, you create a matrix element out of the 2 pathways and which has a phase. So and the total matrix element, so you can think of it as that you can write it down as one part, so you can always rotate one phase out, and then you have one part without a phase and a second part with a phase. And now you can also see that you might or might not enclose a 0, and that you see. I mean, if you look at such a phase, which are, well, you can imagine there is. So these are your tunnel matrix elements. The blue, the bright blue, and the dark blue. So here you have a bright blue that goes from here and the dark blue that goes from here. And if you are in a situation that the dark blue is larger than the bright blue, then by changing the phase, you enclose a 0. In the other case, I don't know whether I have plotted that. No, I have not plotted that. So say if the alpha is larger than the beta, then you will not enclose a 0. So you would not have a non-trivial, topologically non-trivial situation. And so let's now think about how to measure that. So I should also...
This is controlled by the what exact? So the
That's
phase.
good. Mhm. Yeah. No, it's an important point. And I'm just trying to think whether I have that. So these alpha and beta, they depend on K1 and K2. They are functions of K1 and K2, where K1 and K2 are the amplitudes, they kind of give the strengths of the shaking for the lower frequency. That was for the two frequencies,
Okay.
half the frequency and the full frequency. So and one can change this phase here with this relative phase. So there is always a bit tricky which phase is exactly which finally. Because you see here I have a relative phase, but then I have finally a phase here in my effective matrix element. Oops, where was that? That one. That's not the same as a relative phase, but it depends on the relative phase. It is, in a way, it's a mess with the many phases, but they are simply there. Yeah, that's.
So there is also a question in the chat. I don't know if it was recent or this. We are talking about delta zero smaller than U or not?
It doesn't need to be small. It's smaller, but it doesn't have to be on a different scale. It's it's basically to separate out that it needs to be such that this state is not addressed by our driving. So that there is a big enough energy difference, say probably it's more the length of our driving, which might give us energy uncertainty. If we need to drive long enough and our system needs to be stable enough that we can distinguish between those two levels. Otherwise, it can be all on the same scale.
Why are we driving at omega now? Like this U minus delta naught versus just U?
So it's again, what is exactly this frequency? Whether the delta you have to calculate in, and there I need to think again, because you see here, I would say this singlet state, this has the lower frequency, so I have to bring this particle there. Here I again plot it with it being U. I thought that there is this delta as well.
Yes, it's there because I mean it's just to like the diagonal term. So you are going to the initial energy of the state is going to be the one particle here with plus delta, imagine, and the other with minus delta. This is the initial state, energy of the initial state, no interaction energy. When you hop, you are going to have an energy U, but also you are going to change your potential because you are going to go to something that you have two particles in the same lower well. With the other case was one particle down, one particle up, but in the other, when you tunnel, you're having extra potential energy. So you match the energy of the initial state with the energy of the final state with the light. So that's why you choose omega.
Yeah. And I think this is an oversimplified picture, because the delta is not in this picture. So we are resonant with this, driving this. It's just an oversimplified picture. Because, I mean, the process would also work if there was no delta zero, yet to have a well-defined experimental situation, we use this delta zero.
Well, you will have to include more double wells.
We would have 4 states, and it's, I mean, the principle would still be there, but it would be more complicated. Good. And I should also give here credit to Frederick Görg, who actually, came up with the scheme. So that's.
What about
So-
the other way? Oh,
Mhm.
sorry. What
Go
about
ahead.
tunneling the other way, where you tunnel from the right to the left? There you need, I guess, plus delta naught instead of minus
Right.
to be
From
resonant.
here to there. Yeah. Then you drive the other. You drive in the other direction the process.
Do you have both of them simultaneously?
Yeah. It's an oscillation. Yes, it's an oscillation. Absolutely. Yes.
But I think
Tilman,
the
so
question is an oscillation, but what if I put the doublon on the left instead of the right?
Yes, then we would be out of resonance. Then we would not drive anything. That's how it is done. I mean, I think in some data sets that plays a role, and one has to take it into account. But the basic ideas that one doesn't have to take into account. But the energies are not so far away. Yeah, I think it was actually we first had some of the graphs there was not perfect agreement with the theory. When we took it into account, then we got very good agreement. I think that was how it was. Okay.
one question. So we are 10:17. So maybe we want to give some 10 minutes of questions. So maybe if they just start to think about.
Yes. Okay. I just yes. The other difficult part of the experiment. So we might not have that fully, because that's now the question: how do you measure it? How do you measure that you have this phase? So it's the old problem. You think I have my experiment, wonderful, and it should do it, but I have also to convince the referee. The measurement process that is described here. Maybe I'm just a bit brief and try to get the main idea of this measurement process. It's a bit like a Ramsey scheme. So what we do is we prepare our system. Well, we start in the ground state. So this means this is singlet state, kind of on a Bloch sphere, and that's the doublon state. So we start in the singlet. And then we adiabatically on this two-level, think of this as a two-level system. And now we adiabatically drive this two-level system onto the equator. So that it's in a superposition of the singlet state and this doublon state, and has since it's in the eigenstate there, it has a well-defined phase with respect to my drive. And then what we then do is we quench the system by turning off, by switching to another internal state which has no no interaction. And then we let the system evolve under no interaction. And that we do then for different overall phases, and that gives us the interference signal. So we prepare, and then we quench into the other Hamiltonian, which has a certain another the Hamiltonian, the phase points in another direction, and then we get an oscillation of our two-level system according to this quenched Hamiltonian, where we have no interaction. And then we always let it run for, I think, the pi half, And then we measure the double occupancy, so how, and the single occupancy. So how many are in the upper or in the lower state. And then depending on the phase, so now imagine that this the blue vector is somewhere else relative to the red one, then the red one will not go as high, or and that should give an oscillation. And that's what we see in the experiments. Oops. So that's, well, it's basically another plot of that. So here we see the amount of population that we get, and our phase we get out by shifting the time when we start our drive relative to our quench. And that gives us a Ramsey type of fringes from which we can deduce our overall phase of our matrix element. And here that is, well, here are all these different phases. So there is also the relative phase, which depends on, so here is the coupling, our two Ks, our two coupling matrix elements. Oops. I lost my mouse, yeah. The two coupling elements and the relative phase, which gives my waveform of my two frequency system. And then there is one more slide, and then that in a way you can interpret it as a little interferometer. And when I did this interferometer picture, I think Frederick always said, well, really one might think of an even more path interferometer. But I think the basic physics, it gives you have one path, kind of the non-interacting path, and then you go up in with the interaction, you pick up a phase, and then you close the interferometer where you don't have this phase because you quenched your system. And then you see, compared to all the time being non-interacting, so the lower path is all the time non-interacting, and here you are interacting, and then you quench and you close the interferometer in the non-interacting, and that should give you a phase in your final signal, and that is the phase you see here. So it's a little, well, one can think of it as an interferometer, which is not so surprising that there is a link between these fluxes that you get to interferometers, which you might rotate, the Sagnac phase, or you have a magnetic field. So it's not, in that sense, not surprising. And then the measurements, they are very briefly, I just show you the measurements. So these are now the phase measurements, and for we're changing the K amplitude and the driving phase. And these are regions where the beta is smaller, and then here the beta is larger, and then in that way, well, in the whole diagram you enclose a singularity. So in a way very similar as in a Dirac point, or you can look at it as a Dirac point. And this is the direct data, and that is the calculation. And one also gets the absolute value of the matrix element, which in a way is like a Landau-Zener to the higher state. And with this, at this point, I would like to stop, because, well, I still have more slides prepared, because I didn't know how long or not it will take me. But this is just things. The losses. Yeah, but maybe there comes a question to the losses. Who knows?
Yes, great, great, perfect. Thank you so much. So yes, we are open for questions.
In the spirit of having these tunneling with phases and having like synthetic magnetic fields, in solid state, like it's often to get like a sizable value of magnetic flux over like the flux quantum, you need like tens of Teslas of fields. So here with the synthetic fields, what limits can I get like any value of sort of this artificial magnetic flux?
Yes, I think to get a large magnetic flux, actually, in that sense, that problem, it's not, it's solved to some extent, but to have a system where you can create interesting many-body phases with, say, interactions and the large flux, that problem is not solved. So it's not, I mean, in a way, compared to solid state, we have other problems and we solve other problems somehow. That's.
I'm thinking what limits the strength of the flux here, in the sense, since you just have a phase, then I can make that phase like 2 pi on any.
Yes. Yeah, that's not the problem. The problem really lies in the heating. That you then the Floquet drive, you have to be very careful not to heat, and that's not so easy. Or there are different methods, but it's
Jaren?
Yes.
Go ahead, Seren.
Yeah, okay, so my question is, can I use Floquet driving to create effectively infinite temperature state by using heating?
Yes, that's a good way how one can drive the system and create infinite temperature states. And I think there are indeed interesting questions, and also something where one experimentally then one can do experiment theory comparison, because it's a fairly well-defined situation.
Thanks.
I mean, there were also work on negative temperature, but infinite temperature, I think, is a very nice. Of course, within a band, you would like to have it within a band, sure.
More questions?
So I have a question, which is, you motivated a lot of this by synthetic gauge fields. These density dependent phases kind of look like gauge fields, kind of not. Do you want to comment on how close they are to gauge fields, or what the routes to gauge fields might be?
So I mean, for us now, the challenge is to make, if we wanted to, there are two challenges. One challenge is to make the system bigger per se. That's not difficult, but to understand what you then measure. I mean, you could couple, I mean, you could make a ladder out of it, and then that's fine. You could then also think about, how can I construct some gauge theory where the theorists, which the theorists like, and there you have to be a bit careful, and can be difficult how you say localize your particles on rungs and so on. So it might be a setting where you have to add additional either magnetic field gradients or other gradients, and getting a bit more complicated. However, you could also take the approach, I do not always care about Gauss law on these things, but I'm more interested about what is happening in the dynamics if I have these gauge-dependent matrix elements, if I have that. And there are also Jens Uwe Wiese, he for example, actually is well, he's one person who suggested this. So he's very open. Actually, I was surprised we had him here for some discussions. That he is not necessarily a big only Gauss law fan, which can be challenging to build. But on the other hand, in Heidelberg, the one experiment they had a nice simulation of a minimal model.
Was that Jedrzejewski, or is that the right person? Or
I have it. It's on one of my slides. There is the.
Okay, I'll look for it.
Yes, yeah. It's a Pan experiment, but it's actually in Heidelberg.
I know what you mean. Yeah, they had the 4-site plaquettes, or.
No. They have a 70. It's a 70-site experiment. Yes. Yeah.
So this is a new one. He had like, I guess 5 or 10 years ago, he had one.
Yeah. No. It's well, I don't know, half a year, or the time is so difficult these days to to have a feeling for the time. Maybe half a year ago or so. It was a nice experiment.
Great. So maybe last brief question is, maybe you can tell us a little bit about the heating, Tilman, just brief discussion.
Yes, sure. Well, the joke will be short. Who is responsible? Was there a slide? Who's responsible? Well, anyway, who's responsible? There is this Charles Floquet. Well, the joke is that has nothing to do. That's another Floquet, but they were contemporaries. The mathematician was another one. But if you Google first, you get that Floquet. Anyway, so what is responsible? And there is one thing actually, which sometimes we could, for example, see we had this experiment where we could even, by Floquet driving, enhance magnetic correlations by basically, because you can change the U effective, you can tune to the red or to the blue of the U transition, and then you can change your exchange matrix element. And there we could actually show that we get enhanced spin correlation, and there is a paper also by a theory proposal by Dieter Jaksch. And then people were a bit surprised, why does it work for us while they have heating in similar experiments. And what we figured out, what one reason for the heating is actually our lattice geometry, that it's reduced. And here, if you compare cubic with hexagonal lattice, then you can look at the band structure, and that's the cubic. And well, the heating is, for example, you have multi-photon process to higher bands. And now, well, and that you see, for example, you can look at the losses, you quickly lose the atoms, and that's plotted as a function of frequency. And now you can look at the hexagonal lattice. And now my last question to the audience is, why is that so much better, the hexagonal lattice? Why is there less heating? I mean, you see on the right-hand side, well, it's the losses, it's just much less as a function of frequency. So you can unmute. It's the band structure. Here you have, along that direction, you have kind of flat bands and big gaps. So there there are much less multiphoton resonances. But you still have, I mean, you still can hop, of course, around the corner, but not the direct processes. And that reduces the heating. And we did another thing concerning heating is doing a 2-frequency drive. If the problem is excitations to the next higher band, say you drive with omega and then you have a 2 omega process, you can drive in addition with 2 omega with the right phase to cancel the matrix element. And that also works, so that you also with not too strong interactions, you get large double occupancies or spin correlations. Okay, and what I'm not going to talk about, there's many-body, Floquet in many-body systems. Well, another time.
Another time, yes. Well, we learned a lot, so I think it has been great. Thank you so much for the lectures, Tilman. And well, so let's recombine ourselves at 11 for John's Bollinger's lecture. Thank you very much.
Yeah, thank you all very much. And if we meet at a conference somewhere, so please just come to me and then you can tell me, we actually were this summer school, and then we can have a chat. Because these days it's a bit difficult. One would like to know you all, of course. And so please don't hesitate. In the coming years, we will surely see each other on some conference.
Thank you.
Okay, so I wish you.
Bye-bye.
Thanks, Tilman.
Bye-bye. Thank you.
Bye.